All right, hello there. So happy Halloween, depending on when you're watching this. All right, you have to excuse me, I'm a little bit tired because for some reason I recorded this video and it didn't record or something. It got lost somewhere, so this is the second time I'm doing it. So here we go. So a partial derivative is just what it sounds like. It's a derivative of part of the function, so namely the x part or the y part. So when you're given a function, f of xy, or basically z, if you write f sub x of xy, it means to take the derivative with respect to x. And so basically what you're doing is you're treating all the y parts as constants, and so their derivatives are 0 if you need to take the derivative. So when I look at this first piece right here, I will be taking the derivative with respect to x, because that's what I'm doing right here. All right, so on this part, I'll be just doing 10x squared. I'm sorry, 10x to the fourth, and then the y squared is just going to hang on. And over here, I'll be doing derivative of 2x, which is 2, and I'll just leave the y on there. Okay, so I would write f with little sub x, and that would be 10x to the fourth, and then leave the y squared alone. It's just like if it was a constant sitting there multiplied by your original. And then the back part, derivative of 2x, or basically x is 1, and so I have a 2 there. 1 times 2 is 2, and then the y. So similarly, if I have to do the derivative with respect to y, the 2x to the fifth would just sit there, but remember this 2 is going to multiply out front, so I get 4x to the fifth, and then y goes down to y1, plus, and then the derivative of y right here is 1, so I just get 2x. And so that's it. So what, pray tell, do these things get used for? So when you do fx, you are doing the slope of the tangent line in the x direction. So in the direction of the x-axis. And fy is the same, except of course it's in the y direction. Okay? All right, so basically on this picture over here, if you take a look, like this t1 right here, this is the slope of the tangent line in the x direction, so it's basically kind of parallel to the x-axis, and t2 is going to be your velocity or your slope in the y direction, so it's kind of parallel to the y-axis. All right, and so basically it's just broken up parametrically, I guess you can think of in a way. All right, so down below here I have a few pictures. I got this guy right here. This is of our main function, a paraboloid right there. And then I have two views, one of them with x and z up here, and the other one with y and z. Now you can see that looking with x and z, it's a little bit not as steep as this one over here. All right, that's because in this problem you have that extra 2 right there along with the y squared, and so that makes the parabola stretch out more in that direction. So it's like, you know, like a parabola that has a 2 multiplied in front is going to be getting taller faster. Okay, and so it has a bigger slope at the moment, or steeper slope, I should say. All right, so let's see if we want to find the derivatives at 1, 1. So first of all, I have to figure out fx. That would be just this piece right here. It'd be negative 2x. The others are all constants. And then fy would be just using that piece right there. The others are all constants to me, so I get negative 4y. All right, and then at 1, 1. So fx at 1, 1. If I plug in 1, I would get negative 2. I plug in 1 for x because I don't really have anything for y. So over here, fy of 1, 1, I would plug in 1 for x and y, but I only have a y, so I get negative 4. So if I show you on these pictures right here, now the point 1, 1 is going to be on a spot like out on the outer surface, so I'm just going to kind of use the edge instead. So like look at the slope right here. And then, you know, 1, 1 would be here also, but I'm going to use the outer edge instead, and then look at that slope right there. You notice how this one is steeper, right? And look at that, that's because my slope was steeper in the y direction. And then this one right here is for the x. This one was not as steep, that was for my x. Okay, so that's pretty much what's going on right there. So let's go on to the next one. All right, so these are just some notations right here. These are just different ways you're going to see the derivatives written. And so mostly we're going to be using this right here, or maybe that. Every once in a while you might see something like this, but these are the ones over on the right, like this guy, that guy, that guy. It's too much trouble. So like I said, mostly these two things, and every once in a while you see these ones right here. Okay, so when we do derivatives, so remember the next thing you learned in calculus was like the chain rule. So if I just did a simple derivative here of 3x squared plus 7 all to the 5th power, I would do 5 and then put 3x squared plus 7 back, drop that down to 4, and then do the derivative of the inside, so that would be 6x out there, and you could clean that up. Derivative of cosine over here would be negative sine, and leave the 4x alone, and then I multiply that by the sine of the derivative of 4x, which is 4. And so you could clean that up and write it nicer, but that's the gist of it, right? And so same thing happens when you have partial derivatives, okay? So if I'm going to do df dx, so that would be f with respect to x, the derivative, I would do the derivative of sine, which is cosine, and leave this x over 1 plus y alone, and then I'm going to multiply that by the derivative with respect to x of the stuff inside the parentheses. So fx of x over 1 plus y. So really for fy it's going to be pretty similar. Cosine of x over 1 plus y times the derivative with respect to y of x over 1 plus y. All right, but it's these two pieces that are going to be a little bit different to do. So imagine this piece over here. You basically have x times 1 over 1 plus y. So you have x times a constant in a way, because that y doesn't mean anything to you but a constant. So the derivative of x is 1, and the 1 plus 1 over y is just going to hang out. So when I do my derivative right here, my derivative is going to be 1 times 1 over 1 plus y. Okay, so my final answer, and that would just stay there, I would have 1 over 1 plus y times cosine of x over 1 plus y. And I don't know why I wrote those extra parentheses. You could write this multiple ways. All right, so over here, the derivative of this other piece on the side, right here, the y is in the bottom. So it's like you have a constant over a constant plus y, and you have to do the derivative with respect to y. Well, so this is going to involve you doing the quotient rule. All right, so let's get to it. So I have cosine of x over 1 plus y. I need the quotient rule. So that means the bottom has to get squared. The derivative of the top is a constant. So remember, the derivative of a constant is 0 times the bottom, 1 plus y, minus the derivative of the bottom with respect to y would be 1 times the original top. All right, so what I get right there is I get a negative x over 1 plus y squared times cosine of x over 1 plus y. And that is my derivative. They look a little different. Okay, so there's fy and fx. Alrighty. So here's some higher derivatives that you would see, and they're called the second partial derivatives. And so the notation that we're mainly going to use is this stuff right here. Every once in a while, I don't know, you might see something like that. Know that if you see this, it means to do, the derivative with respect to y, and then do the answer on top of that, the derivative with respect to x. Okay, so sorry about that. So just know that. All right, so let's try these down here. So if I want to do fx, the derivative with respect to x, so I have 3x squared. This guy right here, remember that y to the third is just going to sit there, so I basically have 2x, then times y to the third. And this last part, there's no x's, so I don't care about it. So if I needed to do fx, x, I would do the derivative again with respect to x, so I'd get 6x plus, over here the derivative of 2x is just 2, and then y to the third. Then I could do the derivative xy, so this goes to there, but it also goes to here. So now I would be looking at this problem right here and doing the derivative with respect to y. So that means that whole 3x squared out front would just be nothing, and the derivative of the 2x y to the third with respect to y would be 6. The x would just sit there, and the y would be a 2. Okay, so let's do fy. So this part right here would just be dead to me because it has no y's. This next piece, the derivative of y to the third is 3y squared. So I'd have 3x squared y squared minus 4y. Then fyy, I do the derivative with respect to y again, so that'd be 6, leave my x squared alone and put y back, minus 4. Then fyx would be, I would take this guy up here and do the derivative with respect to y. So, with respect to x. So this first part would get me 6x, and the y would stay stay as y squared. And the back part is a 4y, so I don't care about that, so that's just 0. So do notice this. They are the same. We'll talk about that in a minute. And next class, this thing down here, we are going to do some of these problems, just to practice a little bit. Okay? All right, so we're almost done here. Just another couple little things to learn. So this theorem, suppose your function is defined on an open set that contains a point a, b. If the functions fxy and fyx are both continuous, then you'll see what happened here on our last problem. Fxy is going to equal fyx, and that's going to come into play at the very last page as well. All right, so remember when you did in calculus last year implicit differentiation? That was reserved for times when you could not solve for, that were times when you couldn't solve for y. Now in this problem I could solve for y. These two y's right here are pretty simple. I could solve for y if I wanted, but I don't know, just pretend. All right, so let's see. So my derivative, dy dx, like last year, I would do 8x plus, I'd have to split this up and do the derivative of 2x would be 2 and leave the y alone, plus the derivative of y is 1, but it's a y, so I put dy dx, and I leave the 2x alone, minus the derivative of 5y is 5, but it's a y, so I put dy dx next to it, equals the derivative of 6 is 0. And so then real quick, like I would solve that for dy dx. I would get a fraction. So if you can just follow along here, if I was going to solve this for dy dx, my 8x and my 2y would come over, they would both turn negative, and then I would factor out dy dx, and I'd have this 2x minus 5 left over. So let's see if we can just kind of summarize that. I'd have negative 8x, negative 2y, and then divided by 2x minus 5. Okay, and nothing simplifies, so that's done. So we're going to follow the same process, really, and this one truly is not able to be solved for z. So we're going to do dz dx, and then on the next page do dz dy. So, because notice the z to the third and the z, those are kind of embedded there, so you can't really get them away from each other, or away from all the other variables. You can't solve this for z. All right, so here we go. So dz dx. So I do the derivative with respect to x. All the x's are important to me. All the z's are also important, but I'm going to put dz dx next to those when I do them. All right, so x to the third would get me 3x squared, just normal. All right, y to the third. Well, it's like a constant to me. I'm ignoring all the y's when I'm doing dz dx. So I ignore that. The z to the third is plus 3z squared, my derivative, and then it was a z, so I put dz dx next to it. All right, plus, now I'm going to split this off with that z on the end. So the derivative of 6xy with respect to x would just be 6, and then the y just hangs on, and then leave the z alone. Plus the derivative of z would be dz dy. Oh, no, dx, sorry. And then times, leave 6xy alone. All right, I'm really mad at having to do this over again because I already did it once. So I'm kind of irritated, sorry. And the derivative of 1 is just 0. All right, so follow me again. I'm going to be popping those things over to the other side. And then you see if I factor out dz dx, I would have 3z squared and plus 6xy. All right, so if I just do that real quick, I would be able to solve for dz dx. So that means I have negative 3x squared minus 6yz over, I would have 3z squared plus 6xy. And of course, everything there divides by 3. So I'd get negative x squared minus 2yz. And then on the bottom, I would have z squared plus 2xy. And that would be my dz dx. All right, and so now we're going to do the same thing, but on the next page we're going to do it with dz dy. All right, so I don't have my main problem to look at, but I do have it on my paper, and you could have it on yours. So if I'm doing dz dy, remember all x's are dead to me, or just constants. So dz dy, that first x to the third would be 0 because the derivative of a constant is 0. Derivative of y to the third would be 3y squared. All right, plus I'm going to split that next part up in the same way. Oh no, I'm sorry, the z to the third would be 3z squared times dz dy. Plus I'm going to split that problem up in the same way. I'm going to split the 6xy up from the z. And so the derivative of 6xy would just be 6x. And leave the z on there. Plus the derivative of z would be dz dy. And then leave the 6xy alone. And the derivative of 1 would be 0. Okay. All right, so again, solving this for dz dy, I would get negative 3y squared minus 6xz all over 3z squared plus 6xy. And so it looks a lot similar to the last one. It still divides by 3. Yep, there we go. All right, so that would be my derivative of z with respect to y. All right, so this last little bit right here, if a theorem, if f has partial derivatives, fx and fy, they're both continuous around AB. So continuous meaning there's no like domain issues, there's no like fractions where the bottom's going to be 0, like that kind of stuff that would cause problems. So if they're both continuous around AB, then f is going to be differentiable at AB. So it's going to be true that the limit as you approach AB on your function is going to be the same answer from every direction. So remember last section where we had to do all those limits along all those different lines? We don't have to do that anymore. And so therefore, the limit, those 3 little dots mean therefore the limit exists. All right, so we don't have to do that anymore. All right, so there's your homework there, but that's it. That's all I have to say. Bye-bye.